All right, it's one of those topics that I was alluding to in the beginning of the unit that there seems to be, I don't know if the word is contradictory, but it's something in that neighborhood, where you have to learn a little bit about continuity in order to understand limits. But then in order to fully understand continuity, you need to know all about limits. Right? So it's kind of like, how did you have a chance to understand continuity if you needed to first understand limits? So it's one of those things where, like those two concepts, continuity and limits, you don't really have a fighting chance of understanding them conceptually until you have a sense of the mechanics first. All right, but now that we kind of know how to find limits and we have a sense of what it means to be continuous, and really just in a visual sense, all that's talking about is, are there any gaps or jumps or anything like that in your graph? All right, is the graph separated in any location? If so, then it's not continuous. All right, but this is what we're looking at here is an analytic approach for determining continuity. All right, so there's three conditions. It's always three. The rule of three, as that Dodge commercial said. I think it was Dodge. It's got to be defined. F of C has to be defined.
Rule of two.
Ah, yes, master and apprentice. Yeah. Always two there are. So.
Where's the D?
You also, so the function has to be defined, the limit has to exist, and also the last one is the weirdest one. So I'm going to put a little asterisk there. But it's also the most important one. The limit has to approach the point that exists. It's like, whoa, what does that mean? All right. So let me first talk about what C is going to be, because it's saying function f is continuous at C. All right, so C represents some constant for x. All right, and that's always going to be the case. Whole course. C is always going to represent some constant value that would be substituted in for x. All right, so we could take a look at this example here, and we could actually verify, based on these three rules, the two that kind of lead you to the third one. You have really any location along this graph is fair game, but I'm going to take two in particular. I'm going to take a C value first. I'm going to ignore the funky stuff. I'm going to take the C value of -1. All right, so let C equal -1. All right, now normally you're going to be given a C value, but since we're just talking about this for the first time, I wanted to kind of leave it open-ended. All right. So first thing I would have to verify is that f of C is defined. So f of -1, it has to exist, meaning it's not undefined, it's not imaginary. All right, if I look at the graph, I'll bring it in a little bit. If I look at the graph, I could see that there's a clear point here. It's just not like an obvious point like that filled in circle, but there's a point there. It has a coordinate of -1, 2. So f of 1 is actually equal to 2. There's a solid point there. All right, that's a defined value. All right, and like, it's just a weird thing to say. What makes something defined? Sometimes the definition is just related to what it's not. Okay, something is defined if it's not undefined. All right, and we know what undefined means. All right, so that's really what you're looking for. Now, what would a graph look like if it were undefined? You'd be thinking open circle. You'd be thinking asymptote. All right. Now, the limit as x approaches C of the function exists, all right? So That's my second step in the process. I'm going to find the limit as x approaches -1, because that's the c value I chose, of f of x. All right? Now, I don't want you to have to write it out when you're dealing with a continuous graph, because, I mean, you could look at the picture and say, well, it's continuous around that point, -1. If there's a smooth curve that goes through that x value of -1, it starts on the left of -1, it goes through it, and ends on the right of it. Then it's discontinuous after that, but around -1, it's continuous, all right? The limit at a continuous point is just whatever the y value is. So the limit here is going to be equal to 2. So you shouldn't have to do from the left and from the right. However, if you wanted to, you would just be saying, all right, where's my graph in terms of y going as I approach the x value of -1 from the left? And where is it going in terms of y as I approach it from the right? It's going to the same location, the y value of -1. I'm sorry, +2. All right? So our first two conditions are checked. We're good to go. All three have to be checked off in order for this to be a continuous point. All right? So the limit as x approaches c of f of x has to be equal to the limit, the f of c itself. So I'll write that out, but really there's no need to. I'll write it though. X approaches -1 of f of x has to be equal to f of -1. And I could just put a nice check mark there, and the reason I can do that is because I've already verified it here and here. These two values are the same, so I know that the limit and the value are going to be the same. All right, so that's an example of a continuous point. So let's take a look at a case that would not be continuous. All right, so I'm going to choose x, the c value of 2. So let c equal 2. So right on down the line, I'll do f of 2, limit as x approaches 2, of f of x. All right, so just looking at the graph around the x value of 2, what's the y value?
1.
A +1. All right, as I approach from the left and from the right, the x value of 2, am I going to the same place? No. So the limit, complete my sentence, the limit does not exist. All right, so we would conclude here that the limit as x approaches 2 of f of x is not equal to f of 2. So the graph is not, so f of x is not continuous at x equals 2. All right. So it's kind of weird because we're jumping back and forth between c equals and x equals, and ultimately the x and the c represent the same thing. But really, if you think about it, x is any possible point along the graph. When I say that I'm looking at point C, I'm looking at a particular point along the graph of all those possible x values. And then even still, I'm focusing specifically on the c value of 2. All right. Now, this is a counterexample type situation, right? I just went over that concept like a week ago with my Algebra 1 students. So I don't know how many times you've seen it since Algebra 1, the concept of a counterexample. I know you do it again in geometry. I don't know about any time after that. But what it's telling us is you don't look for all the situations where the graph would be continuous. You just look for the cases where it would be discontinuous, because there are infinitely many instances in which this graph would be continuous. If I had to list every single one of them out, I mean, it actually wouldn't take too long. It's just kind of annoying. all right? Just stating where it's discontinuous is much easier. Not continuous at x equals 2, as opposed to saying continuous on the interval of negative infinity to 2, and then 2 to infinity with parentheses all around, with a union in between, all right? Is it terrible to write it that way? No. Sometimes the directions, you just got to be careful. Sometimes it'll say state where it is continuous, and you just have to write it that way. But if you have a choice in the matter, go for the simpler way. Go for the counterexample approach and just state where it's not continuous. It's implied that everywhere else it is continuous. All right? So that was a case of a graph. Sometimes you'll be given situations where you are not given a graph. You're given a function, all right? But that's not too crazy, because all you have to do is determine the graph based off the function, right? Now, if you want to work without a graph, that's fine too. There's ways around that. But you have a calculator, so you're just like a couple of keystrokes away from having the graph, all right? So in the first example, it was like a courtesy to give you the graph. Now it was like, I'm making you do all this work. What's the work? Y equals the square root of 1 minus x squared, for example. I could just type that in, and determine where it's continuous. All right, you see, the directions here are kind of going in the opposite direction. There's the directions, I use direction, the word, in two different ways there. It's a homonym. So direction in two different directions, that was funny. So let's take a look at the trig one, because everybody's terrified of trig. Not really, but hyperbole is also part of the fun. All right, so let's say you're getting a function. Create the graph. Take a look, but if you have to determine the relationship using limits, then the graph will kind of get you pointed in the right direction, but you still have to go from there. All right, so this is the way I handle it. Y equals, well, this is the way everybody handles it, but I'll show you the part that's unique to the way I handle it. So 1 divided by cosine x, because for whatever reason, the people who created this calculator thought it's a great idea to have one whole key dedicated to just a comma, but they couldn't find any way to get reciprocal trig functions in there. I don't get it. So 1 divided by cosine of x. All right, make sure you're in radian mode, and that's specifically because the domain is given in radian form. Now, periodic functions, trig functions, they propagate out to both infinities, negative and positive infinities. So you need a domain, otherwise it's an infinite graph. And so a lot of stuff breaks down if that happens. My first move is to do a zoom trig, and then adjust a window after that. All right, so I have my zoom trig. That'll give me what the calculator thinks is the best x and y axes, the scale, and then I'm making the adjustment based off of what the domain is telling me. Basically, I'm just using the zoom trig to help me figure out the y's, because the x's I already know. I just don't want to think about the y's. So 0 in window, 0 to 2 pi. Oh, that's L2. 2 pi. And then hit graph, and now you have the relevant pieces. And it looks like this graph is broken in two places. Like, it starts on the left, it goes up, then there's a gap, then it jumps down to the parabolic looking piece, and then it jumps up to the exponential looking piece. All right? So really all we have to do is kind of flesh out what's going on here. All right? So the way to handle this algebraically is, and assume that it could be a question that you have to do out, rewrite as 1 over cosine of x equals f of x. If we're talking about a continuous function, we're talking about all the x values for which the function is defined, which means not undefined. So determine values of x that make f of x undefined. All right, so that's just telling me take my denominator and set it equal to 0. Same idea as finding vertical asymptotes. Now we're living in the 0 to 2 pi domain. So if you know anything about unit circle or heart chart, then these are not values that you should have to look too hard to figure out. All right. So where is the cosine function equal to 0 on the unit circle? 90 degrees and, well, if you're going up the y-axis, that's one of them. You could also go down the y-axis. 270, but in radian form, 90 is the same as pi over 2 and 3 pi over 2. Now, you just be careful about the domain because they said 0 to 2 pi, so these are good, but if they said something, you know, try to get cute, say something like negative pi to pi, or pi over 4 to 3 pi over 4, something like that, it might include more or less than what you have here. All right? So these are the bad values of x. All right? So one of the conditions for continuity, and really the work is done in this case, because it says a function is continuous at c if the following 3 conditions are met, all 3 of them. You don't get onto the second condition if you can't get past the first one. F of c is defined. All right, well, we just showed 2 instances where that condition is not met. So, and those are the only 2 instances. So we could assume that everywhere else it is defined. And then, I mean, we're not going to test limits for every single one of those cases. So what we would say is continuous on the interval, and this is where we use the interval notation. It's annoying, but it is what it is. Our interval starts at 0. We're going to go up to pi over 2. I don't want to include the pi over 2, though. So what type of fencing do I use? Parentheses. Then I'm going to pick up on the other side of pi over 2. I'll chuck that little union symbol in between. And I'm going to get up to 3 pi over 2, parentheses again. Little union. Pick up on the other side of 3 pi over 2. And that'll get us the rest of the way to 2 pi. Square brackets, because we can include 0 and we can include 2 pi. All right?
So why can you include those 2 pi?
Because they told us that in the original setup.
Oh.
Yeah. We don't always make that assumption, but when they flat out tell us, then we take it and run. All right. Now, number 6, you know, so I'm trying to give you a taste of each type of problem. So number 6 is convenient to number 3, so we'll just do that one. Piecewise function. They're very complicated to graph on the calculator. They're not terrible to graph by hand. You just don't want to do it, right? I mean, sometimes you have to. If a question says graph a piecewise function, you got to graph it. I mean, I could tell you, spoiler, question number 1 on the test, graph the piecewise function. All right, so you'll have to do it, and you'll get practice with that. It's in the review. So it is what it is. Sometimes you just got to do it, because why? The directions told you to. All right, but here, we just need to establish continuity, all right? Same directions. Describe the intervals in which the function is continuous. All right, so what I want to do first is I want to look at each piece separately. And determine undefined. So I'll determine if undefined. All right, I'll write the 2 functions out just to make it obvious. We have y equals x squared minus 1 over x plus 1. And we have y equals negative 2. All right, y equals negative 2 is a constant function. We're not worried about that one. All right. But the other one, there is a value of x that'll make this denominator equal to 0. What's that value? -1. All right. So undefined if x equals -1. So this is a bad number. All right. Now, there's another little twist when it comes to piecewise functions. They're two separate pieces, right? So one is related to a graph of a rational function, and the other is related to the graph of a linear function. What if they don't connect? Sometimes the two pieces come together and they make a point. Sometimes they make, one is a natural extension of the other, right? But sometimes they're just disconnected, like the graph in the example above at the top of the page. So what we need to do is test the endpoints of each piece to see if there is a disconnect. All right, so we have endpoints here related to the x value of 0. All right, so I take my two functions and just kind of scooch it up a little bit. Now, you could do any amount of this on the calculator, the computation, but you're plugging in 0, so it's not like life-changing in terms of the difficulty level. So y of 0, plugging it into the first function, 0 squared over 0 plus 1. And then y of 0 in the other function. Because one of them would be a hole, but if they're going to connect, the solid point for one of them would fill in the hole. All right? But this one is just a constant function, so it's always going to be -2 no matter what the y value is. So one of them is just a -1. So the y values are different. Y values at x equals 0 are not equal, therefore disconnect. All right, so what we get out of this is that we have two trouble spots for this graph. We have a trouble spot at -1 because it's undefined there. And again, they're not asking what kind of undefined. Is it an asymptote or something else? Turns out it's a hole, but who cares? They're not asking. And in fact, if they did, you just look at the picture. I don't see an asymptote, so it's got to be the hole. All right. So that's one of them. The other one is at x equals 0 because that's where the two pieces end, but they don't come together. They don't merge. All right. So this graph is going to be continuous everywhere but those 2 points. So this is an infinite graph, so it starts off at -infinity. The smaller of the two values is -1, so that's my first stop. Union. My second stop is 0. Union. My last stop is infinity. Well, in a manner of speaking, you can't stop at infinity, though. All right, so looking at number 2, it's asking us to determine, or describe the intervals on which each function is continuous. So looking at number 2, I have a radical function. Now you could get pretty much what you need out of a graph here, but we also want to be prepared to go after this algebraically, right? Because of what I was just saying a few minutes ago. It's possible directions could lead you in that direction, all right? So When you're dealing with radicals, the only thing that can make it a little iffy is whatever's contained underneath the radical. So let's take that expression, 1 minus x squared. Now, I'm going to create an inequality here because I need under a radical only, well, non-negative values. 0 is fine. Anything bigger than 0 would be fine. So I need greater than or equal to 0. All right, so that's cool. I know what the function would be equal to, or greater than or equal to, but I need to figure out what x could or could not be. So let me subtract off the 1. So I'm going to solve this inequality. So negative x squared greater than or equal to negative 1. I'm going to divide out the coefficient, negative 1. All right, so x squared is going to be less than or equal to a positive 1. All right. Now, the next step in the process is kind of on the weird side because it tends to get like overly complicated if you get too notation heavy. But you're going to take the square root. All right. And so when you take the square root of x squared, it just cancels. The radical and the power of 2 cancels, and you're just left with a clean x. All right. On the right-hand side, you're taking the square root of 1. All right. Now, the square root of 1 could be just a 1, but could also be a negative 1. All right. So we're looking for x values that are less than or equal to plus or minus 1. All right, so if you're not careful about that notation, you could lose some solutions. All right. Now, the alternate notation for this, it's kind of cool, so I'll show it to you. And it also kind of works its way into a niftier solution. The absolute value of x less than or equal to a positive 1 is equivalent to plus or minus. It's just something I think in Algebra 2, you probably spent like 30 seconds on that because it was like, oh, and by the way, this is equivalent, and then you never really did anything with it. But the reason why it's pretty beneficial is because this expression corresponds to the interval notation of negative 1 to 1. All right, so it's basically on a number line saying anything between negative 1 and 1, inclusive. All right, so it's kind of strange when you look at it that way, but that's what it boils down to. Now, to get this from that, it's kind of weird. The transition doesn't seem to make much sense. But if you get from here to here, it fits a little bit better. All right. So what a lot of people have done in the past, full disclosure, is they would just say, okay, so if I have x less than or equal plus or minus 1, it's just going to go directly to this form. All right. The reality is, you do all this work, right? And I show you the fancy notation, and you're like, oh, this notation's crazy, I don't want to do it. What are you really going to do in actuality? You're gonna type the function in. You'll do that work to justify or whatever the directions are asking you to do, but then you'll go in and say, okay, I got x less than or equal to plus or minus 1. And you'll say, okay, well, I don't know what the hell that means, so let me see what it means. Try zoom 6. Well, the graph seems to only exist between negative 1 and positive 1. So I'm guessing that that's what my final answer is. Maybe you don't like that. You go into the table with the ordinary settings, 0 and 1 in the table setup. And you see that the graph only exists between negative 1 and 1. So you do that work to justify the problem, like to give the explanation, the algebraic explanation, but then you really go to the calculator to reinforce in your mind what really is going on. All right, so all I'm doing at this point is making sure that this leads to a continuous graph. So that interval -1 to 1, it looks like it's got all the solid points. I go to the graph, it looks pretty solid. I can bring it in. I could do zoom, I like zoom box, because if I go to the upper right hand corner of where I want the box to be and hit enter, and then drag down and over, and then hit enter again, it'll readjust the window just around those points. All right, so it's a little bit, less thinking on my end. That's generally a good thing for me. All right, so it looks like it's existing between -1 and 1. The only thing I would be concerned about with the calculator is, well, what's that gap all about over there? Is that really a gap in the graph, or is that the calculator just being difficult right now? All right, so what you do is you test the endpoints in the function if something like that happens, right? So there's a little funny business on the calculator. So what I would do is I would find f of -1 and f of 0 and make sure, f of 1, and make sure they exist. And they both end up giving 0. So the endpoints are good. All right, so now we've confirmed that this function is continuous on the interval of -1 to 1. All right, just a more intuitive way. We're looking for counterexamples really more than anything else, because the bottom line is, if you're dealing with a function, there's going to be many, many instances of which it's continuous. There should only be a handful of instances where it's not. All right, so you're on the lookout for any gaps, holes, or things like that. I was suspicious of the endpoints, but by testing them in the function and getting real values, I'm no longer suspicious. So I'm confident that my function is continuous on that interval of -1 to 1. All right. You might also have a piecewise function. These are great. I'm going to show you how to handle them by not having to handle them, right? That's the whole idea, because the one thing that people don't like about piecewise functions is the fact that sometimes you have to graph them. The graphing part is the pain. If you could deal with piecewise functions without ever having to graph them, then they're not that bad, all right? So let's see how we could handle this. The first thing we're going to do is look at each function and I'll say specifically each piece of the function. And determine if there are any undefined points or imaginary. Any undefined or imaginary points. All right, so look at each piece of the function, determine if there's any undefined or imaginary points. So I'm using that language on purpose because I really do ideally want you to just look at the two functions and see. Because in most cases, you're not going to have to do any algebra to determine that. All right? So in this case, I would look at the sine function and think what a sine wave looks like. Does it ever have an asymptote, a hole, or anything crazy going on in it? Or is it always a solid, smooth function from beginning to end? Yeah, it's continuous, so I don't have to worry about that. All right? The radical function, are there any x values for which a radical function does not exist? And if so, what kind of numbers would make that happen? So radicals, what numbers are no good for radicals? Negatives. All right, is that relevant here? No, because x is defined as greater than 0, so I'm not worried about the radical function either. All right? So each part is okay. So we don't really have to worry about it. Now, if you had a suspicion, if you weren't sure, if you had a fraction or something like that, set the bottom equal to 0, solve for x, see what's going on. Take a look at the graph, see if you see any asymptotes. All right, so you're using all your resources. All right, the next part of the process is to test the endpoints of the piecewise. So test the endpoints of the piecewise and determine any disconnect. All right, so now we actually have to do something mechanical. All right, so I'm going to take my function y equals the sine of x. And I'm going to take the other function y equals the root of x. My endpoints, specifically x involving 0. It doesn't actually have to get to 0 because the rationale on this is that, let's say we're just looking at the piece that has x is greater than 0. If I were to plot that, I would be plotting it on the graph with an open circle. What I just want to see is, will the other piece of the function fill in that circle? All right, if so, I'm looking at a continuous function. If not, then I'm not. All right, so I'm going to plug those numbers in for x in each of the functions and see what I get. So y of 0 is equal to sine of 0, which is what do we say? 0. Sine of 0 is 0. Cosine of 0 is 1. All right. And then y of 0 for the other equation, square root of 0 is 0. All right. So the pieces connect at x equals 0. All right. So each piece itself was continuous on its own interval. The only place that would have been discontinuous is at the transition from one function to the other. And we just showed that at the x value of 0, they're going to have the same y value. So they're both going to come together at the origin. So we're looking at a graph that's entirely continuous. So this function is continuous on the interval of negative infinity to infinity. I'm just going to talk you through the next example.
Would you, do you include the negative infinity? Yeah, some people do. And either you also point a disconnect, or is it?
No, because that's the y value consistent with the x. We only state the x values for whether it's continuous or not. So the small correction is that that one becomes a 0. There we go.